Assalamu alaikum, thank you doctor for joining us. My name is Marwan Muhammad Magdi, matrix number 208650, and I'm joined here with my partner Farah Zulaika, matrix number 207785, course ECC 3103, Engineering Mathematics, Semester 1, Group 2. Today we're gonna go explain on the applications of matrices in engineering. Specifically in this video, we'll emphasize the application on the 2 degrees of freedom in a spring mass system. Generally, some dynamic systems that require 2 independent coordinates or degrees of freedom to describe their motion are called 2 degrees of freedom. The figure shows a system having 2 degrees of freedom in the same direction but on different masses. For a 2 degree of freedom system, there are 2 equations of motion, each one describing the motion of one of the degrees of freedom. In general, there are 2 equations are in the form of coupled differential equation. Assuming a harmonic solution for each coordinate, the equation of motion can be used to determine 2 natural frequencies or modes for the system. To determine the equation of motion of a 2 degree freedom system, we will apply the knowledge of Newton's second law. From the free body diagram of both masses, we can describe the motion of this system as x1 and x2. The equation can be obtained by applying F equals ma. For mass 1, we have a negative k1 x1 minus k2 x1 plus k2 x2 is equal to m1 a1. For mass 2, we have k2 x1 minus k2 x2, it's equal to m2 a2. Thus, from our equations 1 and 2, we have 2 coupled secondary ODE equations of motion for constant coefficient. Therefore, by using matrix notation, we can rewrite the equation as follows. It can be seen that the matrices M and K are all 2 by 2 matrices and the elements are known M for mass and K for stiffness. We are interested in knowing whether M1 and M2 can oscillate harmonically within the same frequency and phase angle, but with different amplitudes. Assuming that it is possible to have harmonic motion of M1 and M2 at the same frequency, omega, and the same phase angle phi, we take the solutions to the equation as follows. Both equations are differentiated twice to get x double dot or x double dash. The A1 and A2 are constants that denote the maximum amplitude of A1 and A2, and phi is the phase angle. Substituting the above 2 solutions into equation 3, we will get equation 5 as follows. By rewriting the equation before, we can get equation 6 for a non-trivial solution where A1 equals A2 equals 0. The determinant of coefficients of A1 and A2 must be 0, which implies that there is no vibration in the system. Now, in order to solve for non-trivial solutions, the determinant of this matrix must be equal to 0. With this equation, we can solve for positive values of omega, and these solutions for omega are called the natural frequencies of the system. Let's say that these values are omega 1 and omega 2. Firstly, we consider the first row of this expression, which is negative omega squared m1 plus k1 plus k2 times by a1 minus k2 a2 equals to 0. From this expression, we can solve for a1 over a2. The ratio of amplitude to be equal to k2 divided by minus omega squared m1 plus k1 plus k2. These 2 amplitude ratios corresponding to each natural frequencies are known as mode shapes, or sometimes referred to as natural modes. Therefore, we can now prove that the general equation of motion of the blocks as follows. That's all from us. Thank you for joining.